What are we learning? What is calculus? We're learning about the math of change. It's also called the math of infinities, or more specifically, the math of infinitesimals. I don't know how to spell this, so I'm just going to go for it. Infinitesimals. If infinity is like extremely large in terms of its thought process, you know, like continue to add things, add things, add things. What do you think an infinitesimal is? Think like decimal, think like decimal. It's actually something infinitely small, infinitely tiny, okay? A lot of calculus has to do with the thought process behind having something infinitely close to something else, or having something that's infinitely skinny. We are going to get into this concept today, this infinitesimal. Think of a decimal point 0 followed by an infinite amount of zeros before 1. That's what we're going to be kind of talking about that concept today. Okay? Now, calculus solved two major problems in math. And calculus was discovered in the 1600s by two people separate from one another. They're both credited with the discovery of calculus. One you've probably heard of, Isaac Newton, big in physics, also did math in his spare time. And he discovered how to find the tangent anywhere on any curve, okay? It's been done in other situations, but he gave it a more formulaic approach to it. And he did it as well as this other guy, Leibniz. And they did it both in the 1600s, which is a very late discovery in mathematics, considering most of the big things in mathematics are discovered in like the Greek eras and, you know, those Greek mathematicians. They also discovered how to find the area under any curve between any 2 points. And again, it was done in certain situations, but they gave it a formulaic approach. This is called differential calculus, this first problem. And we're going to talk about derivatives. And we'll be talking about derivatives pretty much the entire first semester. Second problem, we call it integral calculus, and we'll be using integrals at the very last unit of the first semester and all of the second semester. They seem like two very separate problems, but they are very much so related to one another. Seems odd that they are related to each other, but we will eventually get to their relationship in the future. Okay? All right, before we get there, we're going to talk about the building blocks of calculus, which are limits. And we are going to start to understand this thing called an infinitesimal. Which is kind of what limits use. All right, and before we do that, we're going to review function notation. So I asked you to graph this function. I'm going to call it g of x cubed minus 1 over x minus 1. And then we have this other function that we don't know the expression for. We'll just call it f of x, and I gave you a picture of it. Now, if you graph that function in your calculator, you should see it looks like a parabola. It's not centered around the x-axis, something like that. I mean, around the y-axis. Okay, it looks something like this. Okay, if we don't see that when we graph, it's because you're not using parentheses. Make sure you use parentheses. All right, now, for graphs of these functions, it's important to understand that, we have inputs and an input axis. We call that input axis our x-axis. Our x-axis is the values, there we go, where we will, take any point on the x-axis, say 1, we'll plug it into our function. Here we're plugging 1 into f of x, and you will see the value associated with the input of 1 is directly above or below that coordinate. And I see I have a point above 1 up here at 2. So if I take 1, I plug it into f, it outputs 2. F of 1 equals 2. The function has the point 1, 2 on its graph. 4, 0. If I take 4, plug it into f, the output is 0. This y-axis is what we call our output axis. Okay, now for this f graph, I don't have an expression, so I just have to look, and I probably would guess about some decimal points, but I wouldn't know exactly because I don't know the expression that created this. But g of x, we are given an expression. We're given x cubed minus 1 over x minus 1. Okay? You don't need to look on a table to figure out what g of 2 is. Okay? You don't need to go into the table in your calculator. You don't need to look at the points and look at 2 and figure out what 2 is going to. How can I figure out the output, and discuss this with your neighbors, or the output for g when you plug in 2? Discuss. Yes, plug it into the expression. Plug 2 in for x. G of 2 is just 2 cubed minus 1 over 2 minus 1, and I get 7 over 1, which is 7. So this graph has the point 2, 7, because when I input 2 for x, you're replacing the x's with 2, you get 7. Okay, cool. I could do g of 0. And again, I could just use this expression and I would get 1. Now your calculator could do that for you. Okay, we did it by hand for both of these. Maybe I didn't show it, but why not keep it up there? We could do it by hand. We don't need a calculator for these easy calculations. But if I had like g of 1.2345, probably wouldn't want to do that by hand, right? If I took that decimal and tried to cube it, it'd take me a very, very long time to do it by hand, right? So this is where we can use a calculator. A calculator can help us do some very complex calculations very quickly because it's got a lot of computing power. Now we can see the computing power of our calculator in the table. It produces really lots of points on whole numbers very quickly, but I like to use trace to show off the computing power of my calculator because I can press trace and yeah, you go left and right and it traces on the graph and that's cool. But I can actually, after pressing trace, pick any number. Like 2. My calculator will quickly do the calculations and go to 7, as long as the number is within kind of the range, the domain that we are using for our graph. So I could do like negative 2.575. Boom, my calculator does that really quickly. That's nice. I can do 1.23456, and my calculator figures out that point very quickly. So that's nice. So computing power, helpful. All right, so let's see, I had 1.2345. Let's put that in, 1.2345. That decimal, 3.758. I'm just going to just stop there, but we know that this would be rounding. Truncating, really. Now, differences between these two graphs is this point right here. We see this like open circle. Now, this is something that's very exaggerated on this graph of F, okay? What this exaggerated open circle is trying to display is that we have values for all of these decimals except for at 3. So like at 3, we are like missing a pixel. And I'm being exaggerated by providing an open circle there. And this open circle says there is no function value associated with an input of 3. Or take 3, plug it into F, and you get nothing. Either blank space or what we'll call undefined. Okay, if you ever just get nothing, you get undefined. Now the graph of G, it looks like we don't have that situation going on. But go ahead and trace over to 1 on the dot. Okay, everybody trace, press 1, press enter. You can even look in your table. In your table, it says there's an error. Okay, but I like trace because it's like 1 for X, Y is blank. Now that's not 0. That means there is no function value when I plug 1 into G. And a way we can see that is if I tried to plug 1 in, I would get 0 over 0. Now, you're not allowed to divide by 0 ever. Even if it's 0 divided by 0, that's not allowed. That value does not exist. It's undefined. Okay? We good with that? So, turns out we have a hole somewhere on this graph of G. My calculator doesn't show it, but it's there. Now, my question is, what location is that hole at? I know it's above 1, but where is it in terms of the y coordinates? Now over here, obvious I can see that this location of this hole in terms of its y coordinate is -1, right? Okay, well, talk to your neighbors. How can you find out the location of this hole? Because if I look like on my graph, like, I don't know, it's like, maybe it's like 1, maybe it's like, I can't really tell by looking, okay? Please, somebody, talk to your neighbor and like discuss an idea you might have for how you could find that hole's location. So maybe we can deal with its symmetry. Maybe it's symmetrical. Maybe you could plug in -1. No, that's definitely not right. Because 1, it looks like it's up here, and it's actually not symmetrical around the x-axis. So symmetry is not going to help us. Okay, other ideas? That's okay. Throw it out there. So what do you mean? Like? Oh, that's a good, that's a good idea, right? But I'm at 0.9, and I get 2.73, and I got 1.06, and there's 3.18. So we got an idea, because it looks like it's skipping over the location, right? Skipping over the location at 1. So it looks like the location's somewhere between 2.73 and 3.18. That's a great idea. So you're not wrong. It's just I kind of want to figure out if it's like maybe at 3 or maybe it's at like 2.9. I don't know. So what should I do now? Remembering that you could plug in any value and your calculator will tell you the y coordinate. That's a great idea. So we're at 0.9. That's pretty close to 1. Let's get closer. Because my calculator can tell me the y coordinate. at 0.99. I could plug in 0.99 in for g because I don't get 0 in the denominator. You're not allowed to divide by 0, but you can divide by 0.01. That's fine. Okay. So now I'm at 2.97. So maybe my answer is 2.97. Should I just stop there? No. What should we do? 1.01. Okay, maybe I go to the other side, 1.01. Oh, I'm at 3.03. All right, so it's looking like it's 3. But how can I be more confident that it's 3?
You go to like 1,000, 10,000?
Yes, get closer. Can we get closer to 1 than 0.99 or 1.01? Yeah. Add another 9. I'm closer. 2.997. That's getting closer to 3. Let's get even closer. Okay, 2.9997. We could have done the same thing on the other side. I still can't plug in 1, right? Because if I plug in 1, I get 0 in the denominator. But plugging in 1.0001, that's allowed because I'm not going to get 0 in the denominator. I'm going to get some decimal. You following me? Now, if you eventually go close enough, and you're like, hey, let's take this to the limit here. Your calculator actually gives up and it rounds. Okay, your calculator eventually after like 9 digits just rounds, and your calculator is going to tell you, oh, that's interesting. You're at 1.3. Now this is actually like a false, misleading thing your calculator is showing you because we don't have the 0.13. When I plug in 1, I have blank space. But if I go really, really close to 1, we're going to get a number very, very close to 3. So that is showing me that this location is actually 1, 3. This is the beginning conceptual idea behind an infinitesimal. If we don't know what's going on at an exact location, well, I can look infinitely close to that location, and maybe I can use that information. Does this make sense? I don't know what's going on at 1. I got blank space. But I do know what's going on if I plugged in 0.9999999. 0.9 with 1,000 nines is essentially 1, but it's not. It's going to output a value that's essentially 3, but it's not. Very, very close to 3, and it's very, very close to 1. We following? This is calculus. We call what we just did a limit. Okay? For f, we said as x approaches 3, I'm going to use this arrow to say approaches. F of x approached -1. As we got close to 3, this function is approaching the y-coordinate of -1. For g of x, as x approached 1, g of x approached 3. Okay? And that's just saying we got closer and closer and closer. It's almost the same thing as saying the whole location. The whole location's at 3, -1. Instead of that, it says, hey, as x approached 3, as we got closer and closer to 3, the y-coordinates got closer and closer to -1, or same with 1 and 3, okay? We're not going to write this moving forward, though. We're going to use different notation called limit notation. And we're going to use a undercase LIM. It says the limit. We're going to use x, an arrow, and then an x-coordinate. I'm going to just use another variable, c. C is an x-coordinate, and it's a number. We'll say the limit as x approaches c of whatever we're looking at, whether it's f or g or some expression like x cubed -1 over x -1 or like x squared -1, whatever it is, equals L. L is just a placeholder. It's a y value. It's a y coordinate. It's a number. Okay? So instead of writing what we just wrote, we would write the limit as x approaches 1 of g of x equals 3. Or the limit as x approaches 3 of this f of x is -1. Okay? Now, I'm picking these locations of these holes as locations that we're focusing on to start with for a reason. It's because, like, I don't have a function value, especially here. Like, I couldn't find where this hole's location is by plugging in 1. Okay, it was like blank. So to find the location of the hole, I needed to go close to it. It's important to understand that if we looked at a different point, where there is a point, like at 1, 2, right here, there is a point 1, 2, that we'd also be approaching that value of 2. If I plugged in 0.99999 into f of x, I'm probably going to get something very close to 2, right? If I plug in 1.00001, I'm probably going to get something close to 2. Typically, function values and limits agree with each other. So I would say that f of 1 is 2, but also the limit as x approaches 1 of f of x is equal to 2. And, you know, that's almost all situations. We're going to look at some interesting graphs with interesting features, like holes, like jumps, because it's those graphs at those interesting locations where things might differ. Okay? So just go with me. I could just give you x squared, and then the limit would just equal the function value, because x squared is a nice curve. It's got the 0.11, and you'd be approaching 1 from both sides. Okay? So knowing that. Cool. Well, when we talk about limits, sometimes it's important to designate which side you're looking at. So when we first looked at this, we started at 0.9 and then 0.999. But then we said, well, why don't we look to the other side, 1.01 and 1.0001. Well, we would consider this two sides of the same limit. We'd have a left side, which would be less than 1, and a right side, which would be greater than 1. And we are going to use notation to denote those sides. So instead of just the limit as x approaches c, I can either use a c with a minus sign in the exponent of c, or c with a plus sign in the exponent of c. This c with the minus sign stands for approaches c from the left. It's called the left-hand limit, LHL for short. And an example of like C minus, if I said, you know, look and do 3 with the minus sign, I'd say look from the left of 3. You would be thinking of using a value like 2.999 repeated. Okay, that'd be just to the left of 3. Does that make sense? Okay. On the other side, this would be from the right. This is the right-hand limit. Or RHL for short. And if I'd say, hey, 3 from the right, you'd be thinking about using 3.0001. Okay, because some situations, the left side and the right side would give you two different numbers. This is an example of, depending on which side of a number you're looking at, you'll get a different value that you're approaching. So we're going to look at g. This is a different g. This is not x cubed minus 1 over x minus 1. Hopefully that's not confusing to you. We're just going to use g now for this different function. And we are going to focus our attention at 1. and we're going to look to the left and to the right of 1. Okay? Now here's what we're going to do. We're going to first start and focus all of our attention on the x-axis, our input axis. I don't look at the graph yet. Okay? I almost pretend like the graph doesn't exist to start. And I focus on the coordinate that I'm looking for. 1 negative, or 1 from the left. I'm thinking about using a value like 0.999, just a little bit less than 1. Okay? Now, I would think, which y-coordinate would I get if I plugged 0.999 into my function? Well, this is what I'm going to do. I'm going to first say, okay, this is to the left. My function values will appear either straight above or below that specific input value. So I'm kind of looking at 1.5 right now. If I plugged 1.5 into g of x, it would output -3. As I got closer and closer and closer to 1, and I'm thinking about plugging in 0.9999, my outputs are still down here at -3. The more 9s I'd plug in, I would still be down here at -3. This is why this left-hand limit at 1 is -3. Now going on the other side, if I went to the right, well, I would be thinking about getting eventually to 1.0001, okay? But let me just start at like 1.5. Again, the output is straight above or straight below this x value. The x value is 1.5, boom. There is my output. It's like -1.5. As I get closer and closer and closer to 1, so if I'm using 1.001, I'm just to the right of 1, my outputs are still down here on this diagonal line, but they are getting closer and closer to the specific value on the line, the end of my line, -2. So this is why I say that this is -2. Let's practice. Flip your page over, go to the bottom left. It says, where do limits exist? Don't worry about that question. Just answer me this. Let's focus our attention for this graph at 2. Tell me, what is the limit as x approaches 2 from the left? And this is a new f of x, so don't worry, it's not like our other one. It's just a new f of x. So what is the limit as x approaches 2 from the left and 2 from the right? Please check your answers with a neighbor. If you don't know, if you're not sure, tell your neighbors you're not sure. Maybe your neighbors can help you. Okay, go ahead, check. Here is 2. X equals 2. Look at your x-axis first. Don't worry about the graph until you start really understanding where your inputs are. Go, check, please. Okay, it's important to think about our outputs being directly above or below our input value. If I get closer and closer and closer to 2, but I'm just to the left of 2, my function values are up here on this line segment. And the closer I get to 2, the closer I'm going to get to this location of this open circle, which is at 1. So this is why I say this one is 1. If I'm to the right of 2, again, start at 2.5. My output for the input 2.5 is directly above or below. In this case, it's directly below 2.5. So f of 2.5 is something like -4. As I get closer and closer and closer to 2, but I'm just to the right of 2, I'm getting closer and closer with my output values to this location, -2. This is why this is -2. Okay? We good? Thumbs up, thumbs down. All right, good. Well, for both of these situations, we can now not use an exponent and just say, what is the limit at 2 in general? If you do not have a negative or a positive, you will say, in general, what's the limit? And since this left-hand limit does not equal this right-hand limit, we say this limit does not exist. Limits either exist or not exist. Function values are either defined or undefined. Okay, go all the way back to our previous example up here. Since this left-hand limit does not equal this right-hand limit, we would talk about the limit as x approaches 1. No exponent means just like in general of this g of x, and this does not exist. Because limits only exist when the left-hand limit equals the right-hand limit. And whatever the value is of that left-hand limit and the right-hand limit is the value of the limit in general. And it equals the shared value. Okay, so let me show you this previous example on the next page. We looked at this example before. As x is approaching 3 from the left of 3, I am down here approaching this y coordinate location of -1. The left-hand limit is -1. If I'm just to the right of 3, my function values are getting closer and closer to this y coordinate location of -1, so this is also -1, which means the limit as x approaches 3 is -1 in general. And now, the way I have this graph drawn, f of 3 is undefined. Now, what if I put a dot up here at 2, and I said f of 3 was 2? Go ahead and put a dot there and say f of 3 is 2. Would that dot change my answers here? Discuss. Fun. Explain why. This dot is just one point. At 3, y coordinate is 2. But if you plugged in 3.00001, you're not getting 2. You're getting -0.99999. If you plug in 2.999, you're not getting 2. You're getting -0.9999. So no, it's not going to change that. Okay? That's just one specific point at one specific location. Limits have to do with what's going on very, very close to the location. Good. Now, we don't have much time, but we have enough time for you to try this out. Now, before we try this out, I'd like you to just go back a page again in this existence of limits part and write a little note to self. Note to self. Typically, and we talked about this before, typically limits exist and they equal our function value at the location that we're worried about. typically limits exist and equal the function value. Take y equals x squared, or f of x equals x squared. Here's x squared. If I asked you what's the limit as x approaches 2 of that y, well, like I have the point 2,4 on the graph of y equals x squared, right? If I plugged in 1.99999 and square it, I'm going to get a value very, very close to 4. If I plug in 2.0001 and square it, I'm going to get a value very, very close to 4. So this limit equals the function value, and this is the case for almost all situations of all graphs at all locations. We are focusing on graphs where we have interesting points, like at -4. I got something interesting going on. Let's talk about the limit there. At 1, I got interesting things going on. At 6, I have interesting things going on. Everywhere else, the limit would equal the function value. Okay? So, keeping that in mind, let's look at these interesting locations at -4, 1, and at 6. Now, I don't want you to be confused. You see this point -4, 2. But over -4, I see an open circle that is telling me that there is no defined function value at -4. Now here at 1, I have a closed and an open circle. The closed circle is telling me you do have a function value. If you were to plug 1 into whatever this function is, this f of x, this new f of x, that if you plugged 1 in, you should get 4. So that's 4. And at 6, you got a point here and an open circle here. Well, this closed circle is saying that f of 6 is 2. Okay, great. We got that out of the way. You guys answer all these limit questions, focusing our attention at -4, at 1, and at 6. What is the limit as x approaches -4 from the left, right, and in general? 1 from the left, from the right in general. 6 from the left, 6 from the right in general. Go and check your answers with the neighbor. Remember, start without looking at the graph on the x-axis. That's your input axis. Don't look at the graph. Look at the values you should be plugging in, and then look above and below that specific value. So -4 from the left. Okay, I should be thinking about -4.0001, plugging that in. Excellent. Help everybody else out. Everybody can check with Ms. Tapana after you get your answers. Good, good, good. Good, 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 good. Check this one again. Good, good, good. Since this doesn't equal this. Good, good, good. You're good. You're good. We'll check this again. I'm to the left of 6. Excellent. Here is my x-coordinate, -4. Okay? -4. I'm going to focus on that. I'm not looking at the graph yet. Okay? So I'm not looking at anything. I'm thinking -4 from the left. I'm going to think about plugging a value in very, very close to -4, but just to the left of it. Then I'm looking above and below that. I got nothing below it, but if I look above it, okay, I got a graph. Where am I really, really close to? This y-coordinate location of 2. That's why this is positive 2. Since I'm approaching 2 from the left of 4 and 2 from the right of 4, my limit in general is 2. Now, from the left of 1, right here, my function values are up here. And we're getting closer and closer to 4, the closer and closer I get to 1, being just to the left of 1. To the right of 1, my function values are down here. As I get closer and closer and closer to 1, my function values are getting closer and closer and closer to that y-coordinate location of -2. Since the left-hand limit does not equal the right-hand limit, this does not exist. Limits either exist or do not exist. Function values are either defined or undefined. 6, yes, I have the point 62. However, if I plugged in 5.99999, I'm up here close to 5. If I plug in 6.0001, I'm up here close to 5. Since this is 5, this is 5, that's got to be 5. Okay? If you're struggling with that, just watch the video of the homework and it'll help you. / come in and see me. All right. Just a reminder, where do limits exist? Typically everywhere. Okay? Here, limits exist for this function for every single x except for 2 locations. This function, where do limits exist? For every single x except for 3? Nope, the limit does exist at 3. It equals -1. So limits exist everywhere for that one. So whenever you see a question asking you, like, where do the limits exist, I don't think you're going to see that on your notes or on your homework. You just first think about they exist typically everywhere. It's only specific locations where they don't exist. All right. Now, we're going to skip this. We're going to come back to this. Go to the next page. Here. If you have a nice, smooth-looking function with no holes, with no jumps, with no asymptotes, limit questions are easy. Okay? X squared minus 1 looks like that. If I ask you, what value is this function approaching as x approaches 2? You don't have to go and graph this and use your calculator and plug in 2.0001. Because I guarantee you, I could tell you very quickly what values those are going to be close to. Who could tell me what value it would be close to if I plugged in 1.999 or 2.001? 3. Why'd you say 3?
I took the 2 and squared it.
The function x squared minus 1 has the point 2, 3. 2, 3 exists. Remember with the x cubed minus 1 over x minus 1? We didn't know what the point was at 1 because it doesn't exist at 1. But this has the function value f of 2 equals 3. I have the point 2, 3. 2, 3. Well, guess what? If I plugged in 1.999, I'm going to get something very, very close to 3. If I plug in 2.001, I'm going to get something very, very close to 3. I didn't have to do that. I don't have to do that because I know what the function value is. And I know that this is a smooth graph. There's no jumps. There's no holes. There's nothing crazy. Okay? Are you okay with that? So other problems that may seem like daunting, it's like, what do I do with pi? Like 3.14 5? Is that close to like 3.14001? Is that below? Like what's bigger than pi? What's less than pi? You could do like pi plus 0.000001 and pi minus 0.0001 in your calculator if you wanted to, but what you will find is that since sine is actually a nice, easy function that doesn't have anything crazy going on with it, if you're looking at pi, I have the point pi 0. If I looked a little bit to the left of pi or a little bit to the right of pi, it would be very, very close to 0. I don't have to do anything crazy here. Typically, limits just equal function values. E to the x, oh no, e to the x, I forgot all about exponents and logs. Well, it's actually a nice, easy function to work with. I know what the function value is if I plug in 2. Guess what? If I plugged in 1.9999 and 2.0001, it would end up with values very, very close to e squared. Okay? Remembering that, if I go back a page to here, and I asked you, what's going on at 2? You don't have to graph this function. You don't have to plug 1.999 in it. You can just plug 2 in. F of 2 is 8 minus 1 over 2 minus 1. That's 7. This is 7. Okay? I don't have to use my calculator at all for that. I do for this. Why? Because if I tried to plug 1 into this function, I get 0 over 0, which is undefined. Please remind your neighbors what you would do, because it's so important, and show it in your calculator to find the limit as x approaches 1 of x cubed minus 1 over x minus 1. Go. Find the limit. Remind your neighbors, please. Tell your neighbors, what do you do to find this limit since you can't just plug in 1? What do you plug in?
0.9999.
Right. Right. What do you plug in, Mr. Montgomery?
0.99.
Yes. You plug in values close to 1. You get values close to 3. Let's do another one really quickly. F of x equals x squared minus 4 over x minus 2. Find the limit as x approaches 2 for this function. Go. Did any of you try to plug in 2 first? No, you didn't. But you're lucky, because if you plugged in 2, you get 0 over 0. Okay. I could have thrown a trick at you and said as x approaches 3. And then if you were all typing in and graphing, you were wasting time. Okay? But regardless, 2, you do have to graph, you do have to use your calculator because you get 0 over 0, undefined value. You end up having a hole for this graph. You need to find the location of the hole. You should be graphing. You should be plugging in 1.99999 and 2.00001, and you should be getting values very close to 4. Got it? Good. You do the same thing for this guy. I can plug in 1. I get root 10 minus 3. I can't plug in 0, but I could graph, use x equals 0.00001. You'd end up with an answer of 1/6. I don't want to spend time doing that. Okay? This function. If I looked to the right of 0 and to the left of 0, you'd see 2 different things. And if you graphed it, you'd be able to see this, but you need to be familiar with this type of function without having to graph it. If x is bigger than 0, I'd have a positive x value divided by itself. What's x divided by x? 1. It is because of that reason, if you are just a little bit to the right of 0, all of your function values are 1. Whether you plug in 3 or 7 or 3000 or 0.001, your y value is 1. This is 1. If x is less than 0, now this is not technically proper, but whatever, you'd have a negative value. If you plug a negative value into this is an absolute value, a negative plugged into an absolute value makes that negative positive. That turns into a positive x, but the denominator would be a negative x value. What does this equal? -1. You would see on the graph, this would be at -1. And this limit would be -1, which means it does not exist. This is the only function that we will look at this entire year that has a jump that is not a piecewise function. We need to be familiar with this function moving forward. Okay? If you have a vertical asymptote, you don't have a limit. I'll just say that. We'll talk more about asymptotes next class, but this graph looks like this, and it's got a vertical asymptote. So like if I look to the right of 0, I'd be approaching like positive infinity. To the left of 0, I'd be approaching negative infinity. This guy, it's a great looking graph. It's very interesting because as I get values closer and closer to 0, I'm dividing by smaller and smaller and smaller things. What would be a number divided by something really small, infinitely small? Like 8 divided by 2 is 4. 8 divided by 1 is 8. 8 divided by a half, 16. What's happening to my numbers? They're getting bigger. As I throw something smaller and smaller and smaller into this, this gets bigger. What ends up happening with the graph is that it oscillates faster and faster and faster. It keeps going through like the sine, the closer and closer and closer you get to 0, and it's because of that that you're actually not going to be approaching a specific value, and that doesn't exist. Not super important to know, but sometimes you'll see this pop up in books, like it doesn't exist because of the oscillating nature of it. Now, piecewise functions. You got to stick with me through this one. We're looking at x equals 2. I'm going to first look at 2 from the left and 2 from the right. All right. Well, it's really important that we understand these pieces, if you looked at them individually, are nice. They're continuous, they're smooth, there's no holes, there's no asymptotes, so I don't have to worry about it. So if I'm looking at 2 from the left, first of all, you're thinking of 1.999. Now, if I were to use 1.999 and plug it into this function, I need to look at this domain and make sure I read, okay, for values that are less than 2, I should be using 3 minus x. Okay, so I'm going to use 3 minus x. And technically, you could think about plugging in 1.999 in for 3 minus x. But you might as well just plug in 2. Hold on. Well, you can go. I'm going to keep talking. You plug in 2, you get a y value of 1. If you're going on the other side of things, you'd be looking at using a value like 2.0001. Well, I'd be using this bottom piece. But I wouldn't plug in 2.00001 because it's the same as just plugging in 2. And I get negative 2. This is why this limit in general does not exist. I'm going to keep going because I'm recording, but you guys can go. Now, if I ask you what's going on at 1, this is messed up. They would think about plugging in 1 into 3 minus x and 1 into x squared minus 6, and they'd say, okay, if I plug in 1 into 3 minus x, I get 2, and if I plug in 1 into x squared minus 6, I get negative 5. This must not exist. But this is wrong, completely wrong, because when I'm using a value like 1, I am using only the top piece. I don't use the bottom piece whatsoever. So don't plug 1 into x squared minus 6. It's not being used. Just use 3 minus x. You would get 2 in both directions, which is why that's 2. Let's look at this one. We have the limit as x approaches 4 of f of x. Well, you should be looking at 4 from the left and 4 from the right. Now, if I'm looking to the left of 4, 3.999, I would be using 8 minus 2x. Now I can plug 3.999 in here, but it's just going to approach what 4 is plugged in there. If you plug 4 in here, you get 0. Okay. 4 from the right, 4.0001. I'm going to use the square root of x minus 4. Plugging this in is the same. It's going to get you values that are approaching 4 plugged in, which gets you 0. Since this equals this, this is 0. However, if I looked just at 2, I would not look at all at values bigger than 4 and root x minus 4. I would not plug 2 in there. I would plug in 2 into 8 minus 2x. I don't have to worry about 1.999 or 2.001 because they would both be approaching the value if I plugged in 2. And this would be 4. Hopefully we understood that. Thank you.